Okay, we're gonna start off with homework 1, Part C, Part 1. We're gonna derive the rasterized equation. So just a little background on what we want the rasterized rice to accomplish. We basically have this flash container. We have some liquid L and some vapor V in there, and it's usually um, a bicomponent mixture here. So you usually have your Z is usually filled with a um, number here and a number there of two components. So, and our goal with the rastered rice is so our flash calculation is to help us with that. So we want our phi, we want to have a way to um, basically find out our vapor fraction, which is just our uh, V over F. And this will help us determine, what components are where and in what phase in our flash. So, in order to start deriving this, we need to start out with a mass balance. So we need F equals V plus L, and then we can go a little farther to this with our F times our ZI, which basically gives us how much of a component is in the feed, and then we can do V and then our yi plus our lxi. Okay, so and the next thing we want to do is we want to use our k constant, and that's equal to our liquid mole or our vapor mole fraction over our liquid mole fraction. And the easiest thing to solve for here is just solve for our vapor mole fraction. Just multiply our xi over, and we get yi equals xik, and then we can sub this in. So we get our f zi is equal to our v xik, and then we have our xik, so of our component, and then we have plus lxi, and then we want to get the zi or our feed mole fraction by itself, so we divide by f and divide by f there and divide by f there. And so you can start to see that our v over f is going to substitute in right here. So we can go ahead and do that. Is equal to our phi, which is our vapor fraction, which is we wanted into the equation, and then our xi ki plus L over f xi. So the problem is we kind of need this all in terms of phi, so we need this LF out of here, and a way to do that is to just take 1 minus phi is equal to 1 minus v over f. And so 1 is basically f over f. That's going to give you an answer of 1. And so we can then plug in for these f's v plus l on this. So 1 minus phi, and since 1 is basically f over f, we have v plus l over v plus l minus v over v plus l. And the v's are going to cancel right here, and all you're going to be left with is L over V plus L, and the V plus L is just F. So 1 minus beta L over F. So we can plug our phi in for our vapor fraction right there. So we have Zi equals our theta, or phi, xi, ki, plus our 1 minus phi xi, and we can factor our xi's out, so Zi equals xi phi ki plus, plus 1 minus, okay, so there's that. And we want to get xi by itself because we know we can take the summation of it, and it's going to be equal to 1 with its mole fractions by itself. So that's what we're going to do, and we get xi equals our theta ki plus 1 minus theta and over our mole or our feed composition. And then so we take the summation of it, and we know that, like I said before, this is going to be 1. All of our mole fractions added up are going to equal 1. So we have 1 is equal to our sum of ki plus 1 minus theta and our zi. And we can help solve for our, and then we can use this to solve for our vapor fraction in order to figure out how much of a component or how much of vapor and liquid is in equilibrium. So we can move this over to Python now and use it for our second part of our homework. I just realized I had this written wrong. We divided by our vapor fractions over here over to our zi, so this should be flipped. Should be zi over theta ki or phi ki plus 1 minus phi, and same thing here. Phi ki plus 1 minus phi over zi. Okay, so that's the correct Raster Rice. I'm dumb. I literally just rewrote what I was trying to change. So zi phi ki plus 1 minus phi. There we go. Okay. Okay, we'll be going over homework 1, part 2, where we implement the Raster Rice equation based on a flash calculation for a 40-60 molar feed mixture of benzene and toluene, and it's at a pressure of 101,325 pascals. And the temperature is at the average of the dew and bubble point temperature. So start out with we have our functions that we used on part B, and these are the bubble point, dew point, dew temperature, and bubble temperature and pressures. So we'll use these functions to help with our Raster Rice. But first we need to set our pressure and temperature. So 101,325, and the temperature was an average equals it is the bubble, yeah, that one. So it's our bubble temperature with our composition and pressure, and we want the zero index because we want the temperature that comes out of that function, not the compositions. And same thing with this one. So see what T gives us. There, yep, looks good. So then we can move on to our functions. So we have currently 2 unknowns in our equation for our Raster Rice, and one is K and the other is phi. And phi is the one we're going to do iterations on to solve for it, and K we can get by doing some algebra. So we know from Raoult's law that our yi is equal to our P saturation, depending on temperature, times our xi over our total system pressure. So if we do that and we plug in our yi in with our k yi over xi, if we plug that yi in there, our xi's cancel out and we're left with k is equal to our P saturation, depending on temperature, divided by our total pressure. So we'll start with that, but we need this as a function first. So we'll do the Raster Rice function, and we need z, p, and t. And then we'll go with colon here, and then we'll go with our k is equal to our saying our r dot p vap at t divided by our pressure. Okay, so now that we have K, we can now start another function, and we can define this as our, how do we want to define this? Let's define it as our so let's just go r theta, or r there. So this one we're just going to need our phi value, and we're going to use our iteration to find our phi through this. Before we do that though, we're going to return our before we do that, we have to first set our Ratchet-Rice equation equal to 0, and that way we can get the total sum for this, and we can plug it into our iterations so that we can use it to force it to 0. So we can do that by, so that'll end up being our np dot sum is, and then our z divided by our phi, and then rk times rk, and then we have plus 1 minus phi. And we'll change these phi's out because we're going to have a phi later. Again, let's make that phi 0 and phi 0. Okay, and then right here we'll well, we need this to be a, I guess we can just return this. We don't really need it as a variable. This is all we want out of this. So return this, and then we're gonna do our optimization or our iterations. So this will end up being phi is equal to sp dot optimize dot root scalar lambda. Actually, we don't want this. We want our function to be r0, and then we're going to use our we're going to do r0, so we're going to do our x0, our guess, and we're going to say 0.44. Let's make a guess, have it close to 0.5, and then we're going to have our method, which is Newton, and then we're going to have our dot root. Okay, and then we'll return. Actually, we won't return anything yet. We'll calculate our, what we want out of this is to calculate our mole concentration, or our mole fractions. So xi, we defined that earlier when we were deriving the Ratchet-Rice equation. It was xi is equal to our composition feed, composition of our feed, our phi times ki plus 1 minus phi. So we'll do that equal to z divided by our phi times k, this is be capital K, not a capital K either, yeah, right. Capital K, and then we want plus 1 and then minus phi. Okay, and then our y is just going to be equal to our k. So we just solved for our x. So now we have k y over x, and so we have our x, we have our k. We can solve for our y now. So y is equal to rk times xi. Xi. Okay. And we want to return our, we'll say our xi, yi, and our phi. And enter. And then we'll test this out. So we'll have our RR, and we'll have our set condition. So Z, P, and T, and shift enter. Shift enter. Okay, so right here we have our X composition of our. This would be our something messed up somewhere. All right, here. And shift enter. There we go. Okay, so wait, still messed up. Where would it? Oh, right here. Shift enter. Nope. Oh, this needs to be -1. -1. Okay, shift enter. There we go. Okay, now it's fixed. We have our, these add up to 1 right here. So we have our Xi, our liquid composition for our benzene, liquid composition or liquid mole fraction for our toluene, and our gas mole fraction for our benzene, and our liquid composition for our toluene. And then we have to put out our phi right here, which is 0.451 or 0.452, rounded up. But yeah, that's it for the coding. So I forgot to kind of quickly go back over what we did here. So we had our functions here that we use to calculate our temperature with our average here, and then we defined our Rascher-Rice equation, but we needed our K, and we needed a function that was dependent on phi that we could use in this optimized root scalar here. So when we gave this x0 value, it told it basically, well, when we plugged in our r0 here, it basically told it that this phi 0 here, this variable, needed to be a number that made this equation 0. And then once it got that, we could use our phi value and return our mole fractions for our liquid and vapor. So that's how that was done, and that is the assignment.